Hello, everyone. It is August the 19th, and it's a truly special day. I have a very, very special guest joining us today, and I've actually been wanting to partner with Dr. Laurence Garvie, Laurence from now on, at ASU. He is at the Center for Meteorite Studies, and he's been gracious enough to join us today on our hangout. And we are going to get a behind the scenes after hours look inside the ASU vault. So we are very pleased and honored to have him with us. I'm going to actually just hand the reins over to Laurence because we did a test run and everything seems to be working just fine from the ASU shielded vault. So Laurence, if you would please, a brief introduction and tell us what the Center for Meteorite Studies at ASU is all about and your role there, please.
Well, look, firstly, welcome everybody. By the way, I just wanted to have one slight correction. On my screen here, it shows me as Ewan Garvie. That is my son. He has obviously hijacked this Zoom account, so it's actually Laurence Garvie, okay? Not my son, Ewan Garvie. I'm fortunate to be the curator for the Center for Meteorite Studies at Arizona State University. We're very fortunate here, and you can look up online, you can look up at our history, and you can see we have a long history here of just over 50 years of being here at ASU. And we have one of the, depends on how you count, one of the largest meteorite collections in a university in the world. In fact, one of the largest collections. And sometimes people say, you know, well, are you number one? Are you number two? It doesn't really matter anymore. I think there's, as we can talk about a little bit later, there are so many meteorites now. I mean, the world right now, if you consider, if you think of like pre-1989, when the flood of meteorites started, you know, I think meteorite collecting and so forth was a much more difficult pursuit because there were so few meteorites out there to collect. Now we have 60,000 plus meteorites classified if you look at the meteoritical bulletin, and I often say to people that only represents the very tip of the iceberg. Really, the things that get put into there are what we consider the interesting things that get classified, and we can talk about classification a little bit later because that's actually a really important and interesting point. But what I'm going to do first, I'm going to walk into the meteorite vault because we were fortunate. We moved into the facility that I was showing you, or I'm going to show you now, about 6 years ago. Prior to that, and for the 50 years prior to that, we were in an old facility on the other side of the university. We didn't have particularly good security, and what we did not have was good environmental controls. And that's important. And actually, I have a really interesting sample to show you in a minute. Show you why environmental controls is important. Before we go into the vault, we are fortunate to have our own prep lab. So we have saws and polishing equipment and things like that. As you can imagine, what I don't do actually is I don't typically cut the really big samples. It's too much hard work, and I leave that for the experts, for those who want to cut really large samples, like, you know, Orange River here. Wow. That would be way too difficult for me to cut.
Yeah, that's actually not an isomat.
Well, no, this was actually cut. If you look at the surface of this was actually cut here at ASU with a bandsaw. But there's just so much hard work to cut those. And so I tend to leave that now to the experts. So we'll send, if I need to get this cut, I would send this off to one or two people who I would trust to cut this. Anyway, so let's walk into the vault. So it's a purpose-built facility. This room here, it was built primarily with safety, curation in mind. Safety and curation in mind. If we look into the vault here, we just pan around.
Man, it never gets old.
And we'll walk around and look at some other things in a minute. So when I talk about humidity control, and I like to point this out as being something that's very important. Humidity control means keeping the relative humidity in the air low at all times. And I'm actually going to show you an example of why that's important. I'm going to take you over here. I'm going to put you down for a minute. I'm actually going to go put some gloves on, and we can talk about in a minute why gloves are important, but I'm going to go put some gloves on, and then I'm going to show you a sample.
Guys, come on. How awesome is this?
Awesome. Outstanding. Thank you so much for organizing this.
I cannot believe I pulled this off.
We wear gloves, and we'll talk a little while why gloves are important, or at least for research specimens. and particularly for certain types of meteorites. But first and foremost, I want to say, why is humidity control so important? And here's a perfect example. Here, I have here a small Canyon Diablo that was bought personally and given to one of our faculty who was leaving a few years ago. And that person, and it's just a normal Canyon Diablo, nothing special about it. But this was given to one of our assistant directors. She moved to the Northeast coast, and within a year, about a third of it had fallen off and rusted. This rusting does not happen in our meteorite vault because the humidity is so low. And this allows us to preserve samples for long periods of time. When we talk about curation, curation is important because if you think about the sort of science we can do now, well, what about the sort of science that can be done in 50 years' time or 100 years' time? And I'd love to provide a particular example of this. Here, let me get a meteorite here. Okay. Here's a small piece of a relatively large meteorite that, who's gonna say which one it is, that fell in 1492?
Campo de Cielo.
Anyone gonna tell me what it is? You can either type it in the chat or somebody can just tell me. Somebody must know.
1492?
Yeah.
That's Weston.
What?
Weston?
No.
Oh, 1492.
1492.
Ensign.
That's right. Perfect. And this is a perfect.
That's massive.
Is it? Okay. This is a perfect example of why curation is important. If you try and get it so we don't have the glare. There's too many meteorites in here. I can't put this anywhere. So this is a perfect example of why curation is important. I mean, think about the level of science that could be done in the 1500s, basic, 16, 17, 1800s, still basic, 1900s, and now. You know, we've gone to the point of view where to the realm of being able to look at individual small clusters of atoms now and be able to tell what's happening, what's there. But think about the science that could be done, let's say, in 50 or 100 years' time. Don't know. So this is an example of why curation is so important. It's important to be able to keep things in an environment that's safe and secure for future generations. I'm going to give you another example.
Laurence, what is your humidity goal inside the vault?
Right now, it's probably about 5%.
Okay.
We actually have an alarm set, so if it does get up to around 20%, then we're notified. So we try to keep it as low as possible. Oh, look at this! I love this. Look at all these Canyon Diablos.
Great.
That's just a small selection. I mean, this is probably a relatively large selection of what we have as large Canyon Diablos. But you know, and other institutes obviously have much larger and more Canyon Diablos. This just gives you a small selection. And in fact, a few years ago, we had this one cut. Now, what I love about this one, this was a few hundred pounds. We had this one cut. We had it cut into one slice here, one slice here, one slice, and an end slice. This was actually cut by Robert Ward for us. He said this was his most difficult cutting job ever. Wow. You want to know why it was so difficult?
Is there hardened carbon?
Diamonds.
Well, we think, and I can actually point to some examples in here. There were actually some diamonds in this one, and we didn't know this was going to be a diamond-bearing sample until the saw hit it. And he said as soon as the saw hit it, it started to bounce. And so every slice took about 18 hours to cut. Plus just for one slice, plus about another 18 hours just to polish it. So if you think 1, 2, 3, 4, 5, 6, 7, 8 times 36. Who's good at math? What is that?
240 something.
That's a lot of hours of cutting. Anyway, let's just look around the vault a little bit. We have over here. This is one of our important areas. These things here. These are our nitrogen cabinets. This one's filled with Murchison. This one's filled. So what we keep in the nitrogen cabinets are basically the carbonaceous chondrite falls. So this one's all Murchison. This one's things like Orgay and Bells and things like that. And then this one is primarily Aguazarkas. Yeah, actually primarily Aguazarkas here. And then this one, which we just got here, I don't know if you can read. Can you read what it says on there?
Yeah, that's the new Indonesian fall.
Yay!
This is the new Indonesian fall. Super, super, super exciting material.
Nice.
So I'll just take one of these out. So these do not belong to us, okay? These belong to Mike Farmer, and he has lent us this material and is allowing us to take the type specimen material, but is also allowing me to sort of look at the samples, be careful with them, of course, and look at the samples so I can do the classification. So
Now, this is a extremely fresh carbonaceous fall. We're talking like a week and a half ago.
2 weeks.
Yeah.
About 2 weeks for this material. So it's, you know, like the other carbonaceous chondrite falls, it's black on the inside. You can see some little small chondrules. It's very friable, this one. So this is what I did yesterday. Oh, by the way, that noise, that's just dry nitrogen going into the nitrogen cabinets. So what we actually keeping the humidity in the nitrogen cabinets, it's not really, you can't really talk about humidity anymore in the right sense, but we're keeping the moisture content of the nitrogen cabinets around 100 parts per million. So super low. In fact, what's really interesting, if you take a Murchison, let's just say you got a nice sized Murchison, let's say it weighs 100 grams in the air. You put it in the nitrogen cabinet, within a week, it'll lose about 2 grams of mass as water vapor that's absorbed onto it just gets replaced by the nitrogen. I was going to show the sample that I don't know if some of you saw. I posted some photos yesterday of some scanning electron microscope images because I started the classification for this new Indonesian fall. And this is what we get the data from. So I take a small piece of, in this case, the Indonesian meteorite, mount it in epoxy on a 1-inch round, and this is the sample that then gets put into the microscope. So this is the actual sample that I acquired those images from yesterday, plus the chemical data, which I haven't worked on yet. So this is part of the classification. So an important part of the classification for this particular meteorite is also oxygen isotopes. And Karen Ziegler at the University of New Mexico will be getting that data over the weekend. And so then hopefully by early next week, I can actually submit the write-up, the classification, to the nomenclature committee for voting. So let's just walk a little bit more around the vault. So we have, okay, let's go back to the beginning. By the way, you can tell I haven't planned this. We're just going to walk around and talk about and look at things. So in the center cabinets here, this center cabinets here, and in these cabinets in here, these are all ordinary chondrites. So if we just open a drawer, let's see, let's just open a drawer and have a look. I'm not sure what. Oh, for instance, okay, here's a drawer. Here's some of our Umbale samples.
Oh.
You can actually see one here with a nice hole in the middle because I had to cut a sample out for analysis. So those are Umbale. So these are all the ordinary chondrites here. We don't have a huge number of achondrites, but these are achondrites. Here, for instance, are some of our, but this is also, we also have some display cabinets. So here's some of our larger Murchison samples, Allende samples. There's one Allende, it's about a 30 pound Allende, and another Allende. And then these cabinets over here are all our Allende samples. Wow. You know, a funny story was, so our founding director, Carlton Moore, he was director for the Center for Meteorite Studies at the time of the Allende fall. In fact, he was director for the Center for Meteorite Studies for about 40 years. And soon after the fall, he said he was working in, this was on the other side of campus, he was working, you know, doing his curatorial stuff. And he was also not just the curator, he was the professor here. He said this guy drove up from Mexico with like a station wagon. And he said, you know, and he said, do you want to come? You know, I've got some meteorites for sale, some Allende meteorites for sale. So Carlton said he went out to the car. He said the back of the car was pushed down onto the ground, so heavy. He opened the back of the car. It was piled high with Allendes. Literally must have been almost a ton of Allende's in the car. And you know, at the time, people weren't that interested. He said, "Yeah, I'll buy a few. You know, I'll buy a few stones." So he probably bought 10 stones, and the guy drove off.
Oh my God!
Can you imagine that nowadays?
Yes.
I mean, unbelievable.
Yeah.
It really is. We have. I mean, to be fair, we have not had a fall like Allende since Allende. We just haven't. I mean,
What makes
Aguazarka
it so interesting to you?
Pardon?
What makes Allende so interesting to you scientifically?
Well, Allende was a good sample. Okay, I've got one over here. Let me just go grab it.
Jesus.
I mean, what made Allende so special? It's a carbonaceous chondrite. Now we always have to be careful with the word carbonaceous chondrite. It's more of a historical term. It does not mean it's necessarily rich in carbon. Some carbonaceous chondrites, like the CKs, have almost no carbon at all. So it more implies a bulk chemistry. That's more what it implies.
Okay.
So the bulk chemistry is primitive. It hasn't undergone any significant chemical alteration from the bulk chemistry of the dust from the early solar system. So what made it so special are these whitish objects, the CAIs here, calcium aluminum rich inclusions. And the work that's been done on the calcium aluminum rich inclusions has shown that they are the first datable, we can talk about that in a minute, solids that formed in our solar system. So if we use radiometric dating, and let's say the most common one would be lead dating from decay of uranium, these are the oldest objects that we can date that formed in our solar system.
Okay.
Now, that doesn't mean that there weren't things prior to that, but we don't have a way to radiometrically date them. So everything in this rock, in this meteorite, and everything in this room, and everything around you is younger in time compared to these white objects, the calcium aluminum rich inclusions. So we often talk about the CAIs as being T=0, time equals 0. That's when our solar system started, even though there were things going on. The sun had just accreted prior to that, and there was probably some chemistry going on in the solar nebula, the molecular cloud, just as it was condensing. But these are T=0. So everything else, the chondrules, accretion of the Earth, differentiation to make the larger planets, everything else occurred after the CAI formation. So
Cool.
What also made the Allende such a studied meteorite, not just because of the CAIs, is because there's so much of it. I mean, I can't remember. Was there 40 tons? Some vast number like that fell and was collected. So it's a huge amount of material, and that's one of the things. So because it's a carbonaceous chondrite and it's so what we call primitive. This word primitive confused me for a long time. Primitive just means a bulk chemistry similar to an aggregate of dust in the early solar system. So it has an approximate, if you looked at the ratios of the elements in here and in Orgay and in Murchison, they all have approximately the same amount. There's some variations, and scientists love to discuss what those variations are. But then if we looked at the chemistry of something else, I'm not going to take this out, like an albright. Of course, it's not primitive at all. It's completely different. The chemistry, the elemental ratios are completely different, implying a different post-processing history that changes the elemental ratios.
Okay.
I'm going to show you another nice CAI because I have another one here that might be easier to see.
That was a big piece of bishop, though.
That's actually, oh, let me get that again just to say. Do you remember when it fell? I can't remember when Bishopville fell. Bishopville is one of the albrights, so it looks white. It's like concrete. And this, I think, is the main mass now. So it fell in the mid or early 1800s. And it's basically, the reason it's white is because it's very iron-free. In fact, this Bishopville and Norton County are the only two meteorites that fluoresce with UV light. because you require, for fluorescence, you require super low amounts of iron in the minerals. Let me put it back. I was going to show see if I have a better example. So here's a, okay, let me just clean off that. Just give me a second.
Mm-hmm. I think there's one for...
The camera's dirty. I said my son uses my laptop for his Zoom classes. Oh, that's better.
There we go. Yeah.
Oh, let me try that again.
Wow, Laurence, you're beautiful.
Oh, much better. Okay. Is that actually better?
Yeah, there's less glare.
Okay. So look at that CAI there. That's a CAI. This weird shaped swan or duck looking thing is also a CAI. Here's another CAI here. And they're important because they really tell us about the first solids that condensed in our solar nebula relatively close to the sun. Calcium aluminum rich inclusions, we know from the types of minerals that are present, condense at high temperatures directly from a vapor. So we know that it was relatively close to the sun when this stuff condensed. Oh, by the way, I found something weird in the vault the other day. Here's some Allendes that have been vacuum packed in a little container, and I have no idea why. Oh. Look at that. Somebody took tiny Allende stones and packed them like this. So I've just kept it like this because I have no idea why somebody would put them in here.
That is so cool, though.
Sometimes I'm still discovering things in the vault that are quite strange. Oh, let me show you. So you've all heard of chondrules. So chondrules are, again, I always like to liken those to, and again, chondrules are one of these weird areas of study that scientists have been studying for decades and will continue to study for decades, and we'll never know how they form no matter what anyone says. The reason we will never know how they form is because we can never go back in time and say, that's how they form. All we can do is take all the data that we have and say, these are the likely mechanisms. Anyway, so imagine I always like to say a relatively large dust bunny. There was a heating event, and what that heating event has been speculated and continued to be speculated in papers year after year after year. But they formed these round, can you imagine this heated dust bunny? It was melted in space. The minimum energy configuration for a blob of melted material floating in space with a sphere. This is the largest single chondrule that I've come across so far. It's actually huge.
Wow.
So that's actually a giant, that's actually a chondrule. And that popped out of Allende when I was preparing a sample.
Dang.
So actually, before we do anything with this, we'd actually like to study this chondrule because it's so huge. But we want to be able to characterize it before we do anything. Oh, anyway, so we hadn't finished going around the vault yet. So on this side of the vault, these cabinets over here, these cabinets are only half full. So one of the things we wanted to be able to do was to be able to allow for expansion of the collection. There's no point building a vault and then filling it up completely, but expansion of the collection for hopefully possible future huge donations. You know, there's people who are, you know, our collection has grown by leaps and bounds, either through attrition, either through I acquire single, you know, bits and pieces, or through a large donation or significant donation. And, you know, there are some reasonably large collections out and even huge collections out there in private hands that one day have to find a home.
Exactly.
So we've allowed for expansion. Let me go open to give you an example here. So yeah, so I hadn't finished. These are all iron slices. So we start from A over here. So one that I classified, I helped partially classify it a few years ago. Oh yeah, I don't want to lift it out, it's too heavy. So all the Aguazarka samples.
Oh.
So, you know, so Aguazarka, oh geez, this one's heavy. Yeah. Arispe.
Oh. Jeez.
And that's a weird shaped sample. I'm not sure if it was rolled around in a stream. More Arispes. Let's do one more. What have we got in here? So, I mean, and not all meteorites are pretty. I mean, look at this thing. All of them. So this is the main mass. This was found in Alabama.
Wow.
That's the main mass of Auburn. So not all meteorites are pretty, and this is why you'll probably never ever see Auburn in a collect, you know, for sale in the collector's market, because there's just, this is it. It's really, really ugly stuff. So, and then we have at the back of the vault, we have these large green cabinets. Okay, the cabinets, I'd say this cabinet here, we'll open one in a minute. These cabinets here, these cabinets here, and half of those cabinets, that's all Canyon Diablo meteor crater material. Now, what we're very, now when I say Canyon Diablo meteor crater material, I don't just mean meteorites. And I'm going to show this is one of my favorite things to show here. So just a slight preamble, really. We acquired our collection from at least the first 700 falls and finds, about 700, from Harvey Neininger. So when Neininger was looking for a home for his collection, and there's a long history, you can read about the history, it's well documented, but it took him a long time to find a home for his collection. And when the Natural History Museum in London, was the British Museum, it's now the Natural History Museum in London, started to acquire the parts of the collection, an effort was made to keep most of the collection here at the US, and it ended up here. Again, there's quite a long history to that, you can have a look at that. But we also acquired, along with the meteorites, we also acquired, since he lived up at the crater for many years, a lot of his Canyon Diablo meteor crater material. Here's an example. This is all impactite material that he collected. So, for instance, this jar of Best Food Real Mayonnaise, his jar of Best Food Real Mayonnaise, filled with
spheroids,
millions and millions of impact spheroids.
Are those his original containers?
And that's why, yes, I've actually kept all of them.
Oh, I love
He
it.
obviously loved Ovaltine.
Oh my God, this is pure history right here.
Oh, you're right.
Here's my favorite. I don't know if they had a puppy, but
Oh, that is amazing.
this is filled with about 20 pounds of
I'm joking on that Hills Brothers coffee can.
and Phil's brother regular coffee.
Oh, that's great.
And we've also got, let me see if I can find the other one. He also, I don't know about his.
Is the boot anywhere easy to find?
About his smoking habits, but we've got lots of cigar butts. So this is all, see, this is what I often say to people, you know, meteor crater is really exciting. It's a relatively recent crater, it's well preserved, and obviously masses of focus has been understandably undertaken on the iron meteorites, but there's much more than just that at Meteor Crater. There's all the impacted material, and what are the consequences of a relatively large impact to the surrounding materials. In fact, I found these in the collection relatively recently. All of these little jars are, with his writing on it, he separated all of this material into different fractions, into different impact type materials. And so this is, in fact, all of this material, in fact, most of it, and this is all full of similar materials, like the shocked, let me grab one of these, like the shocked Coconino sandstone. So this is the shocked sandstone from the crater. And unfortunately, we can't, even though there's an infinite supply, you can't get it. You know, if you've ever seen the crater from space, behind the crater, there's a giant quarry. I mean, we could mine this stuff, but the crater being private property doesn't allow this material to go out. But this is what made, do you remember what made this so interesting, the shocked Coconino sandstone? Anyone remember?
I don't.
It was it was the sediment from which stishovite, the high pressure polymorph of SiO2 quartz, was first discovered here on Earth. And that was the proof of a high pressure shock wave going through the rocks. So if you imagine quartz, SiO2, in fact, there are, depending on the conditions under which SiO2 forms and equilibrates, you can either get quartz, you can get coesite, you can get tridymite, you can get other high pressure polymorphs like stishovite. In fact, there are even other higher pressure polymorphs. So so stishovite is only metastably stable at room temperature and pressure. It's actually stable at high pressures and temperatures, but the transformation from a high pressure to low temperature is inhibited. So it can actually coexist as this high pressure polymorph at room temperatures and pressures.
And that sets a minimum gigapascal level of shock, right?
Yes. And there was actually a science paper that was written, I can't remember when, probably the early 80s, here at ASU, that showed the occurrence of stishovite in these materials. So I'm just having a quick look. Somebody had a good question here. Why are there CAIs in some LL3s? And the CAIs do occur very rarely in some of the ordinary chondrites, but it shows, and we don't know how and why exactly. There's still a lot of controversy and a lot of discussions where the CAIs formed. How did they migrate? Some of them did migrate out of that region and mixed with obviously the primitive carbonaceous chondrite material, but some of those CAIs migrated out of their CAI forming region and mixed into a region where the LL chondrites and some of the ordinary chondrites form. So we do find them, but they tend to be very small and very rare. Okay, let me look at one more question. Let me see. Does ASU grade Allende by how quickly it was collected as far as scientific value of the pieces? Yes and no. I know all the material that we got, the Allende material, was collected very early on, soon after the fall. And Allende stones are still being found. In fact, Mike Farmer showed me one recently that was really fresh. I mean, it was found recently. You cut it open because it was fallen in a relatively dry desert environment. It looks almost as good as the day that it fell. However, if you then do detailed oxygen isotopic analysis, so these are materials that formed in a region of the solar system that's very different from the oxygen isotopes that we have here on Earth. So over time, the oxygen isotopes, so remember we have 3 oxygen isotopes, oxygen 16, oxygen 17, and oxygen 18. And the ratio of those that we have here on Earth is very different than the ratio that we have in, for instance, the primitive meteorites. So if you leave a primitive meteorite here on Earth and allow it to weather, it will slowly over time acquire a more Earth-like set of values. So one of the scientists a few years ago actually looked at Allendes that were collected just a few years ago, and they still weren't Earth-like in the oxygen isotopes, but they were much more Earth-like. In fact, we did a study that was published just 2 or 3 years ago on, let me grab a meteorite, on this meteorite. Let me just get rid of this. So does anyone recognize this?
Aguazarkas?
This is Tissant, a Martian meteorite.
That's Tissant? Oh my God.
I know.
It looks nothing like my micro.
It is one of my favorite stones. But one of the big questions is that when you look at Tissant if you put it in a special microscope, contains indigenous Martian hydrogen and deuterium. And the ratios of the deuterium to hydrogen tell you about water activity on Mars. But one of the questions that we had was how quickly, if you leave this out in the rain, how quickly does it become Earth-like in its hydrogen deuterium ratio? So we actually took small pieces do I have it here? Oh yeah, here's one of them. We took small pieces of Tissant. Here's a tiny piece. It's actually difficult to see. And we put it in the desert for 1 year and 3 years, and then put it in the microscope, just these small pieces. So I left it out in the Sonoran Desert here, drove out into the desert, found a remote site, put it out on one, out in the middle of nowhere where nobody was getting, in fact, nobody would recognize it anyway, would they? And then we collected one piece after 1 year and another piece after 3 years. And we put them in the microscope and we measured the deuterium to hydrogen ratio. And guess what? Within a year or two, all the cracks and all the more porous mineral areas had looked terrestrial. They had lost their extraterrestrial deuterium to hydrogen ratio. So this was a paper we published a few years ago. And again, this is why one of the reasons why curation is so important. And let me just flip this round. So this is where we keep our artisan sample. Now people say, why do I keep it in this, even though it's so pristine in here? Just because prior to the COVID thing, I used to give a lot of tours, and this is just to stop fingers from picking it up, people from picking it. Even though we say to people, do not touch meteorites, they still can't help it. So this is just to stop. It's just an extra layer of protection. Oh, I'd love to show you this. Look at. Okay, let me get this out. This is a ridiculously large piece of this.
And by the way, if you're done studying that one that you left out in the desert, I can take it off your hands.
Oh, really? Oh, thank you.
Yeah.
One of the things I have to remind people, and we can talk about this after. This is important. It's an interesting point. Can I have something from here? The problem is everything in here is state property. You imagine trying to give away state property?
Yeah.
Okay. Look at this meteorite.
Oh,
what is this?
I know what that is.
Anyone else want to? Okay, I'm looking at the chat.
Black Beauty.
Thank you.
Black Beauty.
Yes.
Yeah.
Yes, sir.
Yeah. So this is a piece that Jay Piatek donated to us last year. So it's an astonishing meteorite. Even though we have Martians meteorites, so here we have a piece of Los Angeles. And up behind it we have Lafayette and Zagami and Chassis. Oh, here's probably the rarest meteorite in the collection. When people like to say to me, Laurence, what's probably the most valuable piece from the point of view of value? This is ridiculous. This is our largest piece of Chassigny. This is literally when people, because it's always funny. You've all been. You're all experienced collectors here, so you all know what's difficult to acquire. I had a list from the other day from a new collector saying, I want to get, and there was a laundry list of meteorites, and this was like #1. I said, you can't. Yeah. You could be a multi-billionaire, you can't get a piece. Actually, that's not true. I do know of one large piece for sale.
Wow. Now, what makes Black Beauty so special?
So Chassigny is important, hence, so what I love here, let's see if I can show, okay, so I'm going to show it here. So we're going to do SNC, we're going to do Shirgati, then we're going to do Nakla, this is a nice crusted piece, and so SNC, and Chassigny. And don't forget, that's an old-fashioned terminology for the Martian meteorites now. That's when there were very few. And we now know there's much more diversity in the Martian meteorites. So hence, Black Beauty doesn't fit into the SNC, ALH 84001, the Life Martian meteorite doesn't fit into the SNC. And many of the others don't now as well, but we still use that term. For a lot of the Martian meteorites that are found and classified. So this is a gorgeous sample. In fact, if you remember from the literature, what made this such an exciting material to study was that it's not a deep crustal rock like the SNCs, but it appears to be a regolith breccia of of near surface materials that have been welded together, possibly welded together by the impact that ejected this from the surface of Mars. What's also interesting about it, it does appear to contain a large amount of hydrogen. But hydrogen in the form of several thousand parts per million, fraction of a weight %, rather than tens or hundreds of parts per million that we get in most of the other Martian meteorites. So this is a meteorite that's been extensively studied and will continue to be for decades and decades to come. And what also makes it difficult to study is that every single fragment you look at, since it's a regular breccia, has to be pre-characterized. So every fragment is different. So unlike some meteorites where, you know, doesn't matter whether you look at this centimeter or this part, and they all look about the same. With some meteorites like Black Beauty, every single piece is different. And it actually makes it really difficult and complicated to study. By the way, we have exactly the same scenario with both Aguazarkas and with the new Indonesian fall. They're regular breccias. So when people want a piece to study, you know, they'll write, you know, another institute will write to us and say, hey, Laurence, can I have, you know, 100 milligrams or 200 milligrams for whatever analysis they're doing? I say, yeah, sure, here's a small fragment, but it may not be similar to the material that's been classified, even though it looks similar. So that makes certain meteorites very, very difficult to classify.
Like Almahata-Sitta?
I mean, Almahata-Sitta is an example of, I mean, what is it? I mean, we have a few pieces. I haven't tried to acquire too much of it because other institutes have put a lot of effort into acquiring it. So for instance, we have, what is this stone? This is here's one of the stones that we have. It's just, I mean, it's an andesite, a chondrite type fragment. This one's, no, sorry, this fragment's a polymic urolite fragment. Yeah. Here's a fragment of something that makes no sense. It's just it's metal and sulfide. Remember, they also recently found a bencarbonite stone from it. So it really is, it's one of those meteorites that, you know, when we think of classification, we like to take whatever characteristics, the isotopic characteristics, the petrographic characteristics, the elemental composition, and we like to say, okay, it is a whatever meteorite, CM2. We like to pigeonhole things. And that's what we do is, you know, when it comes to science, we like to classify things. But with something like Almahata-Sitta, it doesn't, the classification scheme that we have put together doesn't work. And the one that I'm working on right now from Indonesia is a perfect example of a meteorite that just doesn't fit into the classification scheme. It's a carbonaceous chondrite, but every piece that I look at is slightly different. Now it's going to depend a little bit on what the oxygen isotopes say. If all the oxygen isotopes from the different fragments that we look at are all Murray-like, so CM-like, then it's going to be a type of CM, but with some anomalous features, but only anomalous to the classification scheme that we set up, which is really revolves around Murchison and Murray. Let me have a look, see if there's any more chat things. That's the occasional message comes up. Yeah, why not classify all the different subtypes in the regular samples to build the database? Absolutely, of course we can. But then still, you know, okay, let's think about the way that we currently classify meteorites. You get it, there's a fall, and we want to give it a name, right? We want to give it a meteoritics. So first there's the common name that we use, so Almahata-Sitta. But then if you look at the way the bulletin is currently set up, each meteorite falls onto a particular class. In order for that name to apply to different classes, Jeff Grossman, who currently manages and programs the database, would have to think of a completely different way of entering that data into the database. And we can do that. It just hasn't been done yet. There's another thought from Mike, comment from Mike Kelly. Is there a thought on how many lithologies are in Black Beauty? I can't give you a scientific analysis to that, answer to that, because I don't study Black Beauty, but just by looking at it, I see dozens, just by looking at it in hand specimen. What do the yellow dots mean on some of your specimens? The yellow dots it's more of a historic thing. It refers to where those meteorites came from, and they actually came from the Amherst collection, the ones with the yellow dots. Mike Kelly, with the isotope ratio of O2 on terrestrial time, is there a correction factor for when precision is desired? I have no idea. I'm not sure if you might be able to with something like with meteorite where you could follow how the isotopic ratio changes, but it's probably a nonlinear thing, so it might be really, really difficult to do with any precision. And terrestrial weathering, somebody just asked about terrestrial weathering. Terrestrial weathering is a hard thing. For certain things, you know, when you look at terrestrial weathering, there's different types of terrestrial weathering. There's isotopic exchange. There's changes in the for instance, the organic chemistry, if we're looking at carbonaceous chondrites. And once, for instance, the carbonaceous chondrites change, they're changed forever. And to give a perfect example of that is if we look at the weathering of, where should I put this? Let me grab a sample here. So if we look at, for instance, this Murchison sample, can you see that? So in this Murchison, depending on how long this has been sitting out in the atmosphere, so before we put it into nitrogen cabinets, for the first 30 years of its life, it sat out. So in the dry of the atmosphere, it just sat out in the atmosphere in the labs. And what happens is that the indigenous extraterrestrial organic compounds change slowly over time. And what actually happens is that that bugs from the atmosphere, you know, if you imagine every breath that you take has bacterial spores in it, has bacteriocysts, and it actually has spores from fungi, so simple microorganisms. They're just out everywhere in our environment. That's just what we are as living beings. Those spores and so forth get into the sample, and with any sort of moisture, let's say on a really moist day, can start eating, it's actually called catabolism, but they start eating your organic compounds. So the meteorite will look completely fresh and normal, yet the organic chemistry changes. And that's one of the reasons why we keep them in the nitrogen cabinets. It basically preserves the organic chemistry forever. I'm going to put, this is actually our largest one right now. And by the way, when people ask us for Murchison for their study, I tend not to supply it to them, even though we have maybe 5 kilos of Murchison. The Field Museum in Chicago has over 40 kilos of Murchison. So just to let people know, there's a lot of Murchison out there. And even though Aguazarka was a big meteorite fall, it still was nowhere near as large a fall as Murchison. Just going to put this back. Oh, let me show you. Okay, this is not our sample. I'm just going to turn the nitrogen cabinets up for a minute because they're very noisy. This is unfortunately not ours, though anybody out there, if you want to buy it for us and donate it to us, I would appreciate this. This is one of the Aguazarka stones.
Wow.
This is Mike Farmer's stone. He's left it here. We're just keeping it in here.
Beautiful. That is crazy beautiful.
It is an amazing sample.
Oh, that's got the blue crust on it too.
Yeah, that blue crust is yeah, I don't know how well you can see it on there, but that blue crust is quite interesting. Blue crust only forms on the trailing edge of the meteorite. Really? So the meteorite was traveling in this direction, and the blue crust formed on the back. So you have the rollover lip all the way around the sample of the stone, and that blue crust. Man. So by the way, the meteorite that fell in Indonesia just a few weeks ago, you know, the house hitter of that stone, that also had blue crust on it. And unfortunately, fortunately, it looks like it was a really big fall, that carbonaceous chondrite in Indonesia, but unfortunately, nobody can go out there. They've got a complete travel ban from any foreigners from entering the country. So there's this at least 5 mile long strewn field. 3 stones have been found. Unfortunately, you can imagine, had this been normal times, you know, there'd be a dozen or so collectors out there combing, and it's dry season in northern Sumatra. There'd be dozens of collectors out there combing the whole area, and we'd have loads and loads of stones. But I think, unfortunately, the vast majority of them are just going to disappear.
Oh, man.
So can somebody ask about, Pat Brown, can you speak about hot form CAIs and cold form volatile rich carbonaceous chondrite? Again, this comes down to, if the CAIs formed early on, and by early we only mean hundreds of thousands, if not 1 million or 2 years before chondrules, there was a mixing of that material, then there was a mixing of that. Again, I have to backtrack even a little bit further here. The early solar system, where the planets are, is not where they are now. we know that when the carbonaceous chondrites were forming, Jupiter was much closer to the sun. And the Jupiter actually formed a gap, which the Jupiter was actually much closer. In fact, it was closer, it might have been as close to the sun as current between Earth and Mars. And all the more rocky meteorites that we have formed between Jupiter and the sun, so the hotter material. And by the way, this happened after CAI formation. And then all the carbonaceous chondrites and meteorites like that formed farther out from Jupiter in a slightly colder region. Where this material accreted was about 1 million or 2 years after CAIs had formed. And there's still this big controversy about where were the CAIs at this stage. So how did they mix in with this material? But so we have high temperature materials like CAIs, high temperature materials like chondrules that then accreted with colder material, colder damp material that formed these early planetesimals that made, for instance, Murchison, that made Aguazarkas. And these things were then allowed to slowly react in a closed system environment while they were still warm. That warmth came from radioactive decay of aluminum-26, but that has it's a very short, aluminum-26 has a relatively short half-life. They only stayed warm for 1 million or 2, a few million years at the most. And then basically were preserved, and basically preserved in the cold of space before they landed here on Earth. So we're mixing high temperature components with low temperature, relatively low temperature formed materials. We think that Murchison formed at about 120 degrees C. At least that's what the minerals and the isotopes are telling us. Let me go through one or two of the other questions. Then we'll take a small break and maybe look at some meteorites. I'm going to have to plug my computer in somewhere in a minute and keep so we can charge it up. So is it possible that CAIs are inherited from chondral precursors? It's the other way around. So CAIs are older, chondrules are younger than us. So it's the other way around there. What is the maximum temperature meteorites should be exposed to, and what period of time would be critical, for example, drying after meteorite cutting? Oh, and that's always such a hard one. I like to, so if I'm cutting a meteorite with water, first and foremost, I always say this is important to people, and I'm sure everyone here knows it, do not cut your meteorites with tap water.
Yes.
Chlorine in tap water is the worst possible thing to touch a meteorite, because it sets up an autocatalytic reaction that allows your meteorites to continue to weather and rust forever. So chlorine is actually one of the worst things. What actually happens is chlorine binds to the metal that's there. It forms an intermediate chlorinated oxyhydroxide compound that over time crystallizes to iron oxides and hydroxides. It releases the chlorine. That chlorine then goes back into the metal and forms more chlorinated oxyhydroxide compounds, which then crystallize. That chlorine then goes back in again. So you must use either distilled water or reverse osmosis water or something like that. But what I tend to do, so we use reverse osmosis water here. Once I've cut, I rinse it with reverse osmosis water. I then dry it. I then typically rinse it in alcohol and then put it in a low humidity environment and just let it dry. And that's the simplest thing. That's the best you can do. You're at a disadvantage if you live somewhere like in Houston, or if you live next to the coast. You're just always going to be fighting humidity. You just always will. Let me take this over here. Oh, here's the microscope. So here's our normal petrographic microscope that I use for looking at the sections. And you can see here's another carbonaceous chondrite down here that I'm classifying. This is a really weird carbonaceous chondrite that we acquired. Here's Saricicek, or Big Goal.
Wow.
This is one that we recently acquired in trade. That's a gorgeous sample.
Yes.
Really. You can just see.
From Turkey.
Yeah, you can just see the interior there.
That's beautiful.
It's a gorgeous sample.
That's a Howardite.
So these are all things that I'm classifying here. These are classification drawers. These are ones where people say, "Hey, Laurence, can you please classify?" By the way, Mike Farmer has his own drawer here, but I can't show you what's in it. Look.
Do I at least have a tray in a drawer yet?
You don't have a tray, but you have. Where's your stuff? No, you look at this.
There we go. Nice.
See?
Wow.
So this is one that I've promised to classify for TOFA. I still haven't.
It's fine.
Now, to be fair, the last few months have been a little bit unusual.
Mm-hmm.
They really have. We've only really had permission to come back to work relatively recently. I was coming in for just to check on things, but like most institutes, ASU was being very, very careful. So anyway, so these are the classification drawers. These are things that I'm working on, partially working on. These are things that I need to finish classifying. Some things are easy, some things are difficult. Some of this is trade stuff. You know, somebody says, "Hey, do you want to have something?" And we may or may not acquire it. Oh, look at this! Look at this meteorite here. This is
Wow. Beautiful.
that is one. That's my. So it's hard. This is my favorite Socotalin.
Wow.
Good. So yep.
I like this one, but I like that one because it's not one of the cleaned ones. So it's one of the ones that was collected very early on. So it still has actual fusion crust on it. Let me show you another one of my favorites. Oh, this we got fairly recently. This was a large, and I mean large, iron fall in Russia in 1990. Oh, jeez. So this is Sterlitamak. And not many people have heard of it, but it made quite a sized crater. And the main mass of the meteorite, because it was just normal sediment, it was alluvial soil. The main mass penetrated 40 foot into the ground.
Jesus.
Wow.
So the way this one was, and they only excavated it a few years ago. And the reason we got this piece is that the backhoe operator who was digging out the hole to get to the main, they knew it was down there somewhere. This was only, you know, what is it, 10 years out? No, a few years after the fall. Again, you have to look up the dates. But the backhoe operator, as he was digging out, he noticed this meteorite roll to this fragment roll to the side, but he didn't tell anyone. He collected it afterwards. And when the guy who owned it, when he died just a few years ago, he gave it to his son, and his son brought it to Tucson, was it 2 years ago? Mike Farmer acquired it.
Mm-hmm.
Mike Farmer threatened to cut it up, and so we acquired it. It was not an easy acquisition. So this piece is amazing because you can see this is just a torn piece. This was torn off the main mass as it penetrated into the ground. So there's the fusion crust, a tiny piece that was taken off for classification. There's the fusion crust on the outside. So this is one of the rare fusion crusted irons. And this is about, apart from the main mass, which I think is at one of the Moscow museums, this is, I think, the only piece outside of Russia.
That's awesome.
Somebody wanted, oh, let me just show you this, and I was going to show you one of the Arizona ones. I love, this is an example of how, this is an iron that was found only a few years ago, and I classified in 3 years ago. So this is called Sauceda de la Borda. This is one of the irons from Mexico. This was found by a farmer who was clearing a new field, and the edge of it was sticking up out of the ground. Now, you know, one of the interesting facts about collections like this is that we have lots and lots of irons, yet irons only represent about 5% of the fall. So why are there so many? And it's pretty obvious. You know, had this just been a stony meteorite, the farmer would have just picked up this stone and thrown it to the side. But he picked it up, realized there was something unusual about it because he could barely lift it up. At the time, it was almost 100 pounds. And he did a little bit of research online, found Mike Farmer's name. Mike Farmer bought it. I classified. Here's the actual donated classification piece from the interior. It's got a beautiful, Wittmann stuff pattern. A nice big troilite graphite inclusion. So I classified it with John Wasson. John Wasson did the chemical work on it, the bulk chemical work on it. And then we are managed through great difficulty to acquire this main mass through a trade from Mike Farmer. So it now resides here. This is, apart from one or two slices that were taken off, this is all of the main mass. But it does show that new irons are occasionally found, and it's much more difficult in a sense for institutes like ourselves to acquire these large irons, because there's a lot of people out there with lots of money, and especially most of the irons over the last 8 to 10 years have been going to China. In fact, almost all of them have gone to China. So very few large irons have made their way into large collections. Let's talk a little bit about, okay, what time are we? So you have to let me know, what are we? We've had almost an hour. What do we want to, we can go through some of the questions in a minute. What do we want to do and over what time frame? Let's see on the chat.
Yeah, I don't have to be at work tomorrow till 9 a.m. So.
Okay. I'm happy to do up to another hour. I've already seen a request for L'Aigle. Okay, let me grab L'Aigle because I know exactly where it is. Have a look at, we're going to look at these in just a second.
I do appreciate everyone joining us today. This is fantastic.
So here's our one of our L'Aigles. I don't know, I have no idea if this is a large one or not. This is one of the L'Aigle stones. And what I love about this is the label that goes with it. Look at this.
Oh, beautiful.
Yeah.
I mean, that, to me, that is as precious as the meteorite.
Yeah. A lot of us collectors go after old labels and museum labels, and, you know, that's beautiful.
Okay, and I was going to show you, let me just put this back.
Mm-hmm.
As somebody said, I'm going to show one before we look at the next meteorite. I was going to just show you why I think labels are so important. And I really value the historic labels that we have. Look at I'm going to try and show this. This is a bit difficult to show. I'm trying to see what you're seeing.
Oh, yeah.
Can you see all those labels?
You can tell the history of that stone.
Yep.
Wow.
So for me, the labels are absolutely as important because they tell about, so this one, I mean, the latest label is the white one at the front, which is ours.
Yeah, that's awesome.
So
Everyone who passes through that rock passes through adds a little history to it.
And, you know, and now the history is, I'm going to have to charge up my computer a little bit. I'm just going to have to move some Canyon Diablos. 1 second. Oh, jeez. Somebody asked about Aztec. I think I have a piece of Aztec, but it's a very boring looking meteorite. 1 second, I'm just going to park you here while I get my charger.
I want to know how I can have those exact drawers installed in my office. I need a
Yeah,
wall
I've been
of
thinking
those.
about that too.
I need an
I
entire
think we're all
wall.
drooling a little bit.
I need an entire wall of those drawers.
It's amazing.
Yes.
With
I'd
glass
like
fronts.
one of each.
Kind of makes our collections look kind of pitiful.
Yeah. I asked Laurence one time about his collection at home, and he kind of chuckled at me and says, I don't collect meteorites.
Why would I? Why would I collect meteorites? And also, to be fair, when with the last director, Minachi Wadwa, and it was one of the discussions that we had. You know, she said it would be very inappropriate for me to have a meteorite collection because there's.
Yeah,
I
what are your priorities?
don't think I would do anything untowards, but you know, to collect something that you're also curating would be very difficult. Let me just go grab it. I think Aztec over here. If I can find it.
Yeah.
To be a reseller, to be a reseller and a collector is also hard.
So Aztec, it's really, I mean, as an ordinary chondrite, it's, see, there's a number on it. There's a little bit. This is all we have pretty much. There's some fusion crust there. I don't know much about this meteorite. You can see some glint of the metal from the ordinary chondrite. So Zagami, someone's asked. We have some, but remember, Zagami. There's some large slices of Zagami out there that are in private hands. So we have some pieces. I don't think they're particularly impressive, but I'll grab a slice.
I just can't get over the size of some of these rocks you got.
Yeah.
Here's one of our
Huge.
Here's one of our slices.
Of Martian Zagami.
Yeah. You can see the shock veins in it.
Mm-hmm.
Mm-hmm.
Oh, I need to change my gloves. That was from lifting up the irons. So that's, you know, it's one of those. It's one of those meteorites, and we have quite a few slices like that. It's one of those meteorites where it was a relatively big fall. It was relatively recently, so there's lots of it available. What makes it? Can you see the deal? Oh my goodness, deal is a. You're not going to be impressed by this at all. Deal is one of those unobtainable meteorites. See if I can find it. Okay, we have. So if I remember correctly, somebody and I would have to look up. I think deal was a single small stone, correct? And what we have, and I think what we have is that. This, you know, for people who are fall collectors, especially American fall collectors, this is an unobtainable.
Mm-hmm.
I mean, I know who has the main mass, but the main mass isn't much bigger than this.
Jeez.
So it was a single stone from New Jersey. I think, did it hit the side of a barn? I don't know, but for that sort of information, you all have, or should all have, this.
Yep.
Right.
Yeah.
In fact, why this is all, I mean, he did an absolutely amazing job. This is I think one of the star books out there. It absolutely is. And there's the research that he put in. In fact, if you have a look at the labels, most of those are all our labels.
That's fantastic.
Frank came here many times to take photographs. Are they all ours? No, I think a lot of them are. I'm not sure if they're all ours. But he did a fantastic job cataloging, writing histories about all the known falls. But what's really interesting when you also look through here are also all the lost falls. There's a lot of falls that just people, you know about it. A stone was picked up and it's just disappeared. So, and that's really frustrating. San Juan de Capistrano that was one of the falls from California. There's a tiny piece of it's a small fall anyway. There's a tiny piece in the Smithsonian. Where is the rest? It's in a drawer somewhere. We don't know where. So, you know, that's always very frustrating. And I've been, actually, San Juan de Capistrano, I've been trying to track down for a few years now. I've pinpointed one of the buildings at U of A is likely to be in a drawer somewhere in there, but they don't know.
Jeez. They need a new curator.
So let's see, what else did people deal? Weathersfield? What's Weathersfield?
Connecticut.
But is it an OC, an ordinary chondrite?
I'm not sure.
Well, first and foremost, let me just see.
It's an L6.
What?
It's an L6 chondrite. Yeah.
Let me just see if we even have it.
That's the 1982 one.
Oh, 82.
Yeah, there's one in 82 and there's one in, I think, 71.
If it was that recently, then I'm going to have to check over at the computers. I don't recognize it. You know, it's collecting, acquiring more recent OC falls. It's very difficult because the values tend to be very high. So the money, especially for recent falls like that, especially US falls, the monetary values tend to be very, very high, but the scientific value for collecting it for a collection tends to be relatively low. So some of those, I've seen some of the US, the more, the post-1980s US falls, and I haven't gone after them unless I've been involved in somehow in the classification, just because they're so expensive, typically. And let me just have a quick talk amongst yourselves for a second. I'm just going to see if we have it.
This is incredible.
Yeah, amazing opportunity. I'm really pleased and happy to have that Lawrence's time today.
This is world class. This is outstanding. It's so cool that you're recording this.
Yeah, and thank you, Topher, for organizing this.
Amazing.
You're welcome, guys. It's honestly my pleasure to present this.
But we must have to work on the name. We have that name is not Wethersfield is not in the meteorological bulletin, so there must be something similar to that.
Laurence, I would love to, and I hope I do this justice, love to hear a little bit about this Cibico Tionse.
Okay. We were very fortunate a few years ago, as you all know most of the story. So I'll just sort of say it in, quickly, but 4 in the morning, midsummer, around 4 in the morning, there was an enormous fireball over eastern Arizona. About 4:30 in the morning, I know people who saw it, left a beautiful trail in the nice cloudless sky. It was recorded on the seismometers in eastern Arizona. It was recorded on various cameras around Arizona and the Southwest. And importantly, it was also recorded on, I don't know which Doppler radar it was, whether it was a Flagstaff, but it was, the falling material was recorded and was seen on 3 separate radar sweeps. And that's important because the radar sweeps showed this mass of material moving, and moving. And from that, because the upper atmosphere happened to be so still, there were no storms, there were no upper level high winds, nothing significant. So basically, where the radar signatures suggested the meteorites should be is exactly where they were. Now, the difficulty with where the radar signature showed the meteorites to be, it was on the White Mountain Apache tribal lands. And this part of the tribal lands was and is 100% off limits, 100%, you can't even get a permit to go on, 100% off limits to any non-tribal members. And so the people who, and I'm not going to go into it, I'm sure you all know, but those who did go out there immediately and collect materials were all found and fined. So it meant that the tribal members were actively looking out for and stopping anybody who wanted to go out there. In fact, really the only way to get out there was you had to go through the town of Cibique, and the Cibique is 100% White Mountain Apache tribal members. So there's no non-tribal people in that town at all. So just driving through you can't drive through the town incognito. So you drive through the town as a Caucasian, you're seen. There's no sneaking to the false side. Anyway, it was we knew where the meteorites were, 100%. So what I did, and it was very frustrating knowing that there's meteorites on the ground only a few hours from here and not being allowed to go and pick them up. So I immediately wrote to several of the tribal people here at ASU who were in the upper level of the administration and explaining why this is important, why we needed to go immediately, and found one of the tribal members here who also had some family on the tribal lands there, and he contacted their tribal chairman and made a case for us needing to go out there for that it would benefit us scientifically, it would also benefit them educationally, to allow a small group of us to go out and search. And, you know, again, you can read the story online. There's a much longer story to it. Within a week and a half, within 10 days, we had Michael Crow, which is the president of ASU, and our legal department here draw up a rite of passage to go onto the land, which then their tribal council all signed. And basically, we got permission to go onto this part of the tribal land. In fact, we were the first Westerners that had, non-tribal people, that had ever been given permission to enter this part of the tribal lands. In fact, this meteorite fell in the most religiously conservative part of their tribal lands. They don't even go out there.
Man.
So we were given permission. Now, we were going to, and it took, by the way, I condensed this into a quick 5-minute story. This took days and 2 weeks of everyday conversation and emails to set this up. So, and again, these things always happen in end of July. It was 114. Even out there was 110 plus every day. So they also had the bad wildfires on the tribal lands. Anyway, we were going to be met by their ranger. They have a tribal ranger and some other members of the tribal council, and we were going to go camp out on the lands where we knew the meteorites were. Even though we didn't tell them we knew where they were, but we said we thought we knew where they were. So when the instruction was to meet at the end of the paved road outside of Civic Hue at 10 in the morning. And so we met, we phoned up the park ranger, and he said, unfortunately, they couldn't meet us because of the wildfires. They were currently dealing with the wildfires, but he still gave us, he said, you know, if you know where to go, you know, you have permission to go in and camp for a few days and search for meteorites. So we went out and we were given 3 or 4 free days to go and camp out there. So we camped for the first few days where we initially found the small meteorites. But what's really, really annoying is that in the radar signatures, there's one big signal.
Oh, man.
We know there is at least one or more larger meteorites out in the canyon lands, but this is the most unbelievable difficult land to hunt. So the first area was up high, it was amongst the scrub forest, so we just looked for little patches of ground. And the only thing that looked like meteorites, that weren't meteorites, were the rabbit poo. Rabbit poo looks exactly like a small meteorite. It's the only thing that is small, round, and brown. Nothing else out there is small, round, and brown, except meteorites and that.
Carbonaceous lupus.
I mean, you know, the number of times you go, oh my goodness, there's a meteorite, you walk over and it isn't. But so the first area we hunted where the small meteorites are, we found, what is it, 18 or 20 or something like that in those several days of hunting. And then we decided for the last day or so to then see if we could hunt for the larger meteorites. But it's totally, totally impossible country to hunt. Just impossible. Wow. And I'll show you do I have it out on display? One of the larger, here we go.
It's the only meteorite named in the Apache language.
Yeah, so actually, that's an important thing. So normally meteorites are named by the local town or some geographic feature, but I wanted the Apaches to have a name that meant something for them. And by the way, it was very, as a non-native, as a non-Apache, they don't want to talk to us. They didn't want to talk to me. They didn't want to have anything to do with me. And it took a lot of persuasion to get them to, in fact, when I was speaking to one of the tribal members about the meteorite and the scientific significance, he said, oh, that's not what's significant for us. And I said, well what? He said, well, for them, it was some sort of extraterrestrial event that fell on the site, and they have their own interpretation. I was really interested and said, well, what does it mean? And he said, well, that's not for you to know.
Oh.
They have, you know, they have their own philosophy regarding what this meteorite means. And they're not interested in the science at all.
Wow.
So here's one of the stones.
There she is.
And none of these stones, no stones are owned by any private individuals that I can name. Now, the frustrating, one of the really frustrating things about this meteorite is there's lots more out there.
Yeah.
And in fact, they are going to look as fresh as this meteorite is now because it's low metal. It's got almost no metal in it. You know, you could take the coordinates, and in fact, we never hit the coordinates. You can take the coordinates, as long as you don't get caught, you can go out there and find meteorites.
Wow. And this is even more amazing because I witnessed this, and it was on my birthday, June 2nd. So it is a super special one to me.
And it's super special to us as well. I mean,
Yeah.
this is a spectacular, it really is a spectacular meteorite. And frustrating to know that there's, you know, if we went out, now that we know exactly where the small ones are, and we could grid the whole area, we could probably find 100, maybe 200, maybe more over the course of a few days. They're just there on the ground.
If you need an unpaid intern, let me know.
Well, you know where you got the coordinates, just don't get caught.
I don't play those games.
Oh, good luck with that.
Yeah, I do not mess with the tribal authorities. That is their land.
And I'm going to
Need
show
to
you another.
recruit a bright young person from their tribe to get interested, take a couple classes, and then go find them.
We've tried, and I had a set of high school students here from, so there's White Mountain Apache tribe, tribal lands, and then the ones right next door, it's also Apache tribal lands. Anyways, I had a whole group of kids from one of their high schools here, and we were talking about science, and we were talking about the importance of science, and I showed them these meteorites, and I was trying to get them, because they can go, they're tribal lands, so they could go, and I was trying to get them enthused about it, and I said, by the way, that one stone you probably sell for $1,000.
Gladly.
Still no interest. They're just a completely, and I'm not chastising, I'm not saying their way of thinking is wrong, just a completely different way of thinking about things.
Yeah, different line of thought.
Let me show you another meteorite, another Arizona one.
I think he's Irish.
You know, this meteorite, in fact, you all know about, this is the other one that fell in Arizona, you know, just only a year or so ago. Glendale was an amazing, it is absolutely spectacular. So late one evening, I was looking at my emails, and I got an email from somebody from the valley that says, is this a meteorite? And they're holding up this black rock. No, at first he sent me a text saying, I think I found a meteorite. I said, of course you did.
Yeah.
And, oh, I found a meteorite in my garden. I was like, yeah, sure. And then he sent me a photo of this meteorite in his hand. And I was like, yes, that's a meteorite. That's a beautiful fusion crusted meteorite. He said, it fell in my garden here in the valley. And I was like, of course you did. Of course that happened. Because of course I didn't believe him. But he said, no, seriously, you know, and then we were talking back and forth, and he said, no, seriously, he said, I've got a flash on my dad. He has one of these doorbell with a little camera, and it records whatever it records the video. And he said, when I look back, there was this flash. And he said, a few days later, because he didn't often go in his, like a lot of people, they go from the house into the garage, they get in the car, the garage door opens, they drive off. Anyway, he went out into his front garden. And here in Arizona, we have a lot of, I call xeriscaped, not xeriscape, which means dry land gardening. Xeriscape means just gravel, nothing else. And he said in the middle of his garden was this black rock. And he was annoyed. He thought, who threw this black rock in my garden? And he picked it up, and he had enough. And I really credit, I think his name is Cody, for knowing enough about science to think, I think this is a meteorite. And he sent me the photo. Anyway, later that, after we had this back and forth exchange, and he said, no, seriously, this was in my garden. And, you know, and I said, okay. I said, well, let me make some inquiries. So then I sent Robert Ward a text. I said, Robert, have we had an event here in the valley in the last few days? And he said, and he got back to me, a few minutes later. He said, funnily enough, we did. That we had and then we went back to look at the AMS site for that. And he said, you know, there was a reasonably large fireball event in the Northern Valley. You know, a few dozen people saw it. One person said they saw some sonic, heard some sonic booms. And then, so we got the time signature from that. And then we looked in the Doppler radar for the North Valley, and sure enough, in the Doppler, in two of the sweeps, are these signals, because it was a nice clear sky. And when you extrapolate from those signals, basically where this guy lives.
God. And it was a single stone fall. As far as we can tell.
We've only ever found one.
I hunted it for days.
And there will be more. there will be more.
I looked everywhere. I looked everywhere. There's no more.
Come on, it was 100 and teens. We were walking around the roads,
Yeah.
looking at the sides of roads and in people's gardens for days. We didn't find. And we
Did you
didn't-
check your garden, Topher?
Yeah.
And we didn't get arrested. And I went on to the news and said, people send me looking. And I told people where the strewn field is likely to be. I said, send me photos of black rocks that weren't there, which was a mistake. I got hundreds of black rocks. Most of it was asphalt for people's gardens.
Yeah.
But a really curious feature. So then about 2 weeks after that, this guy said, hey, look, I got this hole in my roof that wasn't there. And we looked at the strewn field and, we extrapolated from his strewn field. He was in North Phoenix. And he was still on the line of the strewn field. And then he has one of these 1950s, really shallow roofed houses. And he doesn't have any trees in his garden. And he has, in the 1950s houses, they also had these quite thick, it's like roof slats, really thick. And there's this beautiful hole about this big.
Wow.
So it wasn't like a falling bullet. Nobody could have shot it. But it was right in the corner that we couldn't, and since he was on the strewn field, both Robert Ward and I tried, we had this much space in the attic on top of all the fiberglass to search. We could not search. And we know that somewhere in his attic is this meteorite, but we can't get it.
Oh my God, I'll buy the house.
Offer him a free installation for new fiberglass insulation, twice as much. For free.
So it's now patched up, and Robert and I, it's as I said, when you have this much space, that's the maximum amount of space that we had, and then it slopes down like this. So you could, if you're lying on the fiberglass, you couldn't reach. You could just see the edge of the house where the hole was. And we took magnets on a stick and we poked back there. And we came out all itchy and sweaty, but no, we didn't find anything.
What we do for science.
I know. But unfortunately, but anyway, yeah.
I guess.
But what was really important? No, but what was really important? What for me, what made Glendale so amazing and exciting is it almost fell with no fanfare at all. No giant sonic booms, no holes through roofs. Had Cody not found that one stone in his garden, we would never have known about it.
Jeez.
So when I worked out, if you look at fall statistics, so approximately one fall per square kilometer per 10,000 years. That's the ballpark figure I like to use, and it's approximately correct. Plus or minus 50%, plus or minus 100%, doesn't really matter.
Yeah.
That's an approximate fall statistic based on all sorts of evidence that you could look up on the literature. That means in Arizona, we have about a dozen falls a year.
That's how Chandler happened.
Yeah. So most falls are like Chandler. Just remember, last year we had 3 almost certain falls here in Arizona. 3 big fireballs with sonic booms, with Doppler radar, none of which have been found. Isn't that, so I find that quite astonishing.
Yeah, man, I need to hop on that.
Yeah. So look, let me look through. Amazing story. Working name for the new Indonesian one. I think Mike gave me a name. It's a really nasty sounding name. It's one of these names that's like, ugh, why would you name a meteorite that? Oh, you want to see? Let me get my favorite meteorite.
Nice.
I've got to find it first. Okay. So this was from, I classified this for Keith and Dana Jenkinson. Let's see, what is the notes I have here? Oh no, brought in by Larry Atkins. March 2013. Oh, large piece is a donation by Keith Jenkinson, smaller piece for analysis. So this was a meteorite they brought in. It was from northern Arizona and found by, by the way, who finds the iron meteorites? Gold prospectors.
Oh, yeah.
Yeah. So they brought in this meteorite. It was going to be called Burrow Creek. It was an iron. nice new iron. It's not Canyon Diablo. The structure is completely different.
Yeah.
And I looked at the map and I said, there's Burrow Creek. And then I looked at the map and I said, it's right next to the town of Nothing.
There we have it.
We have to call it Nothing.
Yes.
So this meteorite is called Nothing.
The
I've
meteorite
been
goal.
looking for a piece of that for a year.
Yeah.
So this is it was actually a nice meteorite, but yeah, Burrow Creek would have also been quite good, but come on, Nothing.
Yeah.
So I find, it's like Giblet Winzelwan, the carbonaceous chondrite from Morocco. I classified that with Hasna Shanui from Morocco, and she wanted to call it Giblet. And I looked at the map and I said, come on, Giblet Winzelwan's much nicer. She said, Winzelwan just means hills. I said, nobody knows that. I said, Giblet Winzelwan sounds much better than just Giblet. That sounds so much like something from a turkey. So anyway, we ended up with Giblet Winzelwan. So I thought, even though a name is just really important, names I think are fun. So I like when it comes up with names, I like to find a name that is reasonably, sounds good. It also has to be appropriate as well.
Yeah.
Well, the name Almahakasita just means train station number 6, right?
Yeah. So the reason they named it Almahakasita, apart from there, it's in a very remote region where there's just no names for anything. So it's a large desert region. There might be so that's all. That always, naming can sometimes be problematic. The NOMCOM has the final say on a name. They look at, Jeff Grossman in particular is very careful with names. It has to follow various naming conventions. And if you look at the NOMCOM, their guidelines, most of the guidelines, nothing to do with about classification. The 30-page document all has to do about naming. And naming can sometimes be very controversial, especially if it's a meteorite that is found in a desert region, for instance. So there's huge, long, in fact, the most controversial one that still annoys me, and I'll get it. This gorgeous meteorite from Niger.
Tested 004?
Yeah. I fought hard and for over a year to get this meteorite classified. And actually, it should even be the beginning, the foundation of a book where I fought with the NOMCOM for a year on trying to get this meteorite approved. And I'm not even going to go into the story. It would take me an hour to tell it. But it finally got classified as Tacidet 004, which is an incorrect name.
How's that?
Because it should be Chifadine, but they would not accept that name. Tacidet 004 only applies to the one large stone that I don't have. So that name does not apply to any of the material floating around in the collector's market.
Yeah.
But it's one of the times where the nomenclature rules were adhered to in a very silly way, in my opinion.
Okay. I would like to get your opinion. I know you haven't been doing like the isotopes and everything, but on Check 002, the new ungrouped A chondrite, like that is a stone that you and I would have, kept in our pocket while rock hounding, but definitely not thought of as a meteorite. No fusion crust, doesn't look anything like a meteorite we're familiar with. Do you have any information that you can share with us?
It's one of those, I mean, what you said is absolutely true. It's one of those meteorites that does not look like a meteorite. And even if somebody, when we have our public events, if somebody had brought that to me, I would have said, no, it's not a meteorite. If I saw that out while hiking in the desert, I'd say, no, that's not a meteorite. But it was the detailed chemistry. And did they do oxygen isotopes? If they did oxygen isotopes, I think they did. It was those extraterrestrial things have oxygen 16, 17, 18 ratios that are just not terrestrial. All the terrestrial materials, no matter what the geological processes, fall within fairly tight constraints. The extraterrestrial materials are all outside of those values. So it's the oxygen isotopes will say, hey, this is extraterrestrial. And what it's really done for me, it broadens my horizons of what meteorites should look like.
Yeah.
And I'm hoping now that other collectors have seen this, they'll go, oh, I've seen something like that, you know, and, you know, but the problem is, you know, the bottleneck in all of this is the classification, and especially if oxygen isotopes need to be done. Because there are many, many labs that do oxygen 16 and 18. Lots of labs do that for environmental purposes. Very few labs do oxygen 17. It's a much more difficult, it's a rarer oxygen isotope. So there's only 2 or 3 research labs in the world that do it. Nobody can get it done commercially. And so that's really the bottleneck for a lot of these analyses, which makes it very difficult. And, you know, and I remember I had this conversation with Mike Farmer. He had this wonderful stone. Oh, I mean, in one of his collecting trips in Oman, he has this beautiful story is where he picked up this stone that he says, oh, just a terrestrial stone. He threw it on the ground and they camped or whatever it was. And then when he got up the next morning, they were packing up and he picked it up again. He said, no, it's just a stone. He put it on the ground. Last minute he said, oh, he just threw it in the car. And he didn't think about it. And they got back and they unpacked this, you know, back to the US and they unpacked their stuff. And he looked at it again. He said, why have I got this terrestrial rock? And anyway, for some reason, they cut it open and there was a tiny, tiny speck of metal in it, which indicated that it was probably meteoritic. And finally, it was analyzed, turned out to be a one-of-a-kind rare meteorite that he just happened to pick up for something caught his attention. And I asked him one day, how many other meteorites did you see that didn't see? What I mean.
Oh,
you know,
don't ask.
For example, if you look at the Curiosity rover images from Mars right now, these beautiful laminated layered rocks. Yep. Obviously, if you saw something like that in the desert that had fusion crust, you'd recognize, say, hey, there's something weird. But allow that to weather for a few years, the fusion crust is gone, you see this layered rock, you're not going to pick it up. It doesn't look like a meteorite. So, you know, there is this, we are constrained by, oh, I'm going to show you a beautiful example of when I saw this, and I don't show this to the public because I don't want them to see this.
VIP access, guys.
If I find
We have so much trouble too on the meteorite or meteorong, or is it a meteorite page of people, you know, showing things. And yeah, I erg check wouldn't have made the cut there.
How about this for a piece of slag? We've all seen slag, haven't we? Beautiful, beautiful piece of slag. It's a meteorite.
Wow.
It's willow bar.
It is.
Oh yeah, there.
When you look at the outside, it's an impact melt breccia that just has this beautiful slag-like appearance. If this had been brought into me, I would not have recognized this as a meteorite. But I don't show the
plastic float.
Yeah, it looks even on the side here. It looks exactly like the features you see from the slag from blast furnaces.
Yeah. With brittle fracture.
Wow.
Yeah.
So I don't show this to people because this is a gorge, because, you know, I'd say about 90% of the meteorongs that are brought in are pieces of slag, you know, and I understand why people pick it up. It looks odd. It doesn't fit the surrounding rocks wherever you find it. So it's an odd material. And there was also, if you look at the NASA website, there's a Martian lunar that looks like pumice.
Yeah, Apollo lunar.
Yeah, no, this is a, sorry, I meant a Antarctic lunar that looks exactly like a piece of pumice. I mean, it would, if I saw it in the desert, I would never pick it up as a meteorite. Right, let's see what time it is. Okay, let's do another 10 minutes. How's that? Somebody asked, do we have any of the Ordovician fossil meteorite? No, I don't. There's lots of it available. I mean, I've never tried to acquire any. Falls from Scotland. Can you name one? I'll see. Strathmore. You know, probably not, because they're going to be very, you know, any of the UK ones are very, very rare and very difficult to get. In fact, the one that I got, let me just show, what was this one? This one was probably I think one of the hardest ones to ever get. It just became available one day. The single stone fall from Ireland, Leyland Bridge. I mean, this is an unbelievably rare slice. Somebody just happened to have a slice. You know, so, you know, we all know with meteorites that if something comes up and it's rare and you really want it, you got to get it.
Yep.
Because if you wait, it's gone. And I've waited. Sometimes I thought, yeah, there's quite a lot of it, or, oh, it's too difficult or too expensive, and it's gone. And once it's gone, it's actually gone.
Yeah.
You know, I mean, the perfect example of that is, you know, are all the Sutter's Mill stones. You know, Sutter's Mill, here's a, you know, it was difficult because Sutter's Mill was very expensive, even at the time. Sutter's Mill was a ridiculously expensive meteorite. I mean, the cheapest we got any of it was, we did a part purchase for the main mass stone, and it was $400 a gram. I know that's super cheap, but when you're talking about a large stone,
Yes.
We acquired that with several other institutes. But the next cheapest we got was $800 a gram. And then I tried to acquire various materials right up front, and now it's impossible to get.
Yeah.
You know, even it's only 900 grams. It's 100 stones, though. Almost 100 stones, 90-something stones. So it just disappeared. And it's one of those things that, you know, when there's a, you know, I've now realized when there's a recent fall or something weird comes up, get it immediately, because once it's gone, it's gone.
Yeah.
Somebody asked for Weston, what do we have?
Yeah. Like Zobe is another example of a meteorite that may not be as available as it should. It was probably about a total up to 20 kilos of total known weight, but I think at least 6 or 7 kilos were confiscated by the Pakistani government.
Which one?
Zobe.
Job, yeah. I mean, Mendy got that big stone recently, and you know, I think if anyone, I don't know what his prices are, and that's up to, between you and him, but get it now, it'll be gone once it, because it literally is only 1 or 2 stones, and it's a gorgeous, gorgeous meteorite. And it's one of those stones that in a few years it will be impossible except as some micro somewhere. So here's some Weston stones.
Jeez.
Yellow, so it came from the Amherst collection. And this was if I can't remember how big a fall, but it was a humongous fall. But it was a long time ago now. So we've had, you know, well, 150 years or longer for this thing to you know, disappear into collections and into institutes. And you know, part of the difficulty is when Carlton Moore was the curator, you know, in the late 60s, 70s, and 80s, trading was easier. You know, somebody would come in with some nice meteorites, and he'd say, "Oh, I'd like that, that, and that." And they say, "I would like that, that, and that." They would just do a trade immediately, off they would go. But trading now is far more difficult, partly because at that time there were relatively few meteorites around. Now there's so many that what should an institute like ours focus on?
Exactly.
We can't. Like Church number 2 is a perfect example. Should we try and acquire it?
Mm-hmm. Yeah.
There's 30 kilos of it. Why do we need it? Why should we, this is more of a rhetorical question, why should I try and acquire it for the collection?
Yeah.
You know, so I'm not saying it's not the most wonderful meteorite in the world. It might be the most wonderful meteorite in the world, but we can't acquire every new interesting meteorite that comes up. There's just too many of them now.
Yeah. Yeah. As a collector myself, I'm forced by real estate and budget as well. Yeah.
So for me to do, let's say somebody says, "Hey, Laurence, here's a 1 kilo herb check. I want, I don't know, $10,000 for it." Well, we don't have $10,000. We're a state university, so we have $0 to purchase meteorites. But I could try and do a trade, but then I have to do an audit-proof trade, which just is so difficult, time-consuming, and frustrating. I can do it if there's a really good scientific reason to do it. But it's one of the most difficult things that I have to do. If I have to, a trade that I have to do like that is just.
I know that's a I know that that's a pain for you, but it's a great safety net for science in general.
Oh, yeah.
You can't have someone rape and pillage a collection.
Yeah, because once something is gone from a collection, it's gone.
Yeah.
It doesn't. So yeah, we have to make sure that what we're acquiring into the collection, if we're giving away something, has more scientific value, and there's also other rules, and financially it also has to work in our favor as well. So, you know, it's a hard. It's not impossible, but it is very difficult.
Awesome. Do we have any other
Laurence,
questions in the chat?
Yeah. Laurence, could you speak to the possibility of auditing a class through video or even physically?
Yeah. ASU is one of the more amazing universities right now that is doing more and more and more online. In fact, we just launched our first completely online astronomy degree. You can do the whole degree from beginning to end online. Now, one of the questions that I had, Marissa, you're there, you were asking about doing meteoritics. Hi, Marissa. Nobody teaches a degree in meteoritics. It just doesn't exist. So we only do a meteoritics class. It's actually called cosmochemistry, once every 2 years. And it tends to be just a few students who have already done petrology and have already done mineralogy and have already done isotopic geology, et cetera, and they're the few students that have an interest in meteoritics. There currently is not any auditable online course of meteoritics. Now, there ought to be, and it could be that in a few years. In fact, we had a faculty meeting on Monday morning. In fact, we had a half-day faculty meeting discussing what should we teach in the future. You know, what should we be offering in the future? And one of the things was, how do you offer a component of meteoritics and all the other things that go with meteoritics, whether it's astronomy, you know, understanding asteroids, the future topic of in situ resource utilization on asteroids. You need to have an understanding of meteorites, but you also need to have an understanding of geology. And so, you know, it's not really, you know, I don't have an actual answer to your question, but it's an evolving field. And as I suggested to Marissa the other day, study chemistry, basic mineralogy, basic petrography, basic isotopic geology, you know, isotope geochemistry. You know, really all those basic courses that you would take to study geology, really all meteorites are rocks. That's all they are. It's just a rock. But it's a rock that formed, okay, 4.5 billion years ago, but they're formed under slightly different geochemical conditions that we have here on Earth. So it's still just geology.
Well, Dr. Garvie, on behalf of everyone present and everyone who's going to be watching this on the YouTube replay, I would definitely like to offer my hearted thank you for your time and your information and your generosity. The goal here is to obviously share our love, our passion, and your knowledge of meteorites with the world and see if we can't get more med heads involved. So we're going to draw this hangout to a close without a show and tell today, but I would like everyone to please unmute yourself. Everyone, please unmute yourself. And we're going to together offer thank you to Dr. Laurence Garvie at ASU for his time. Thank you so much.
Thank you very
Thank you
much.
so much.
Thank you so much.
That's awesome.
Lawrence.
So why don't, you know, one of my suggestions would be, you know, depending on what, you know, what's happening over the next 6 months or so, why don't we meet up again in 6 months or so, you know, because obviously there's lots more to see, there's lots more to talk about. If there's interest, you know, we could, you know, there'll be new meteorites by that time. You know, we've only, you know, I've seen there's lots of questions. Sorry if I was not able to get your question or show you your favorite meteorite. So, you know, maybe 6 months from now, year, I don't know, something like that. That's really up to you, Topher.
I'm thinking a slumber party actually in the vault would be great.
Yeah, sleep over in the vault.
Billy,
No, yeah, we got Billy in the house, everyone.
Billy.
Yeah,
Hey.
absolutely. I will
Really?
continue to stay in contact with you, Laurence, and we'll definitely get a follow-up set up. This was most gracious of you, and I look forward to future participation.
Yep.
Thanks.
Okay, everyone.
Thank
Thanks,
you
guys.
again.
Have a good night, everyone.
Thank you so
Thank
much.
you, Lawrence.
Thank you.
Bye, everyone.
Have a
Thank
good
you,
night.
Lawrence.
I'm seeing a
Bye,
bunch of thumbs up and
Topher.
everything.
Hi,
Bye.
Take care.
Michael.
Have a great night,
Later.
everyone. Bye, Lawrence.
Thank you again.
Later, Topher.